This is the message USS Nautilus radioed at 11 in the morning on January 17, 1955, as she got underway from Groton, Connecticut. Underway on nuclear power. 4 words that closed 100 years of submarine engineering. Nautilus was the result of a decade-long effort driven by one man, Captain Hyman Rickover, the naval engineer who would become the father of the nuclear navy. Rickover's insistence on a pressurized water reactor design over every competing concept is the reason this story goes the way it does. Every diesel submarine before her ran on the same rules. To cross an ocean, you needed fuel, hundreds of tons of it. A World War II fleet boat carried roughly 380 tons of diesel for a 2-month patrol. A modern conventional submarine still hauls something in the same ballpark. Burn it, replace it, repeat. Nautilus carried something else. The reactor compartment held a charge of enriched uranium, a fraction of the mass, a fraction of the volume. Her core was good for tens of thousands of miles before the first refueling. Today's American submarines, Virginia-class and Los Angeles-class, do better than that. They never refuel at all. Same job, different rules. This is the engineering decision that made that possible, and the physics that lets a charge of uranium small enough to fit on a single pallet do the work of 1,000 truckloads of fuel. Here's the number that makes everything else in this video possible. 1 kilogram of pure uranium-235, fully fissioned, releases roughly 24 million kilowatt-hours of heat. 1 kilogram of diesel fuel, fully burned, releases about 12 kilowatt-hours of heat, 2 million to 1. That's the ratio at the heart of every nuclear submarine in service. The difference comes from where the energy is stored. Diesel burns by rearranging chemical bonds, outer shell electrons swapping places between carbon, hydrogen, and oxygen atoms. Each rearrangement releases a few electron volts of energy. It's the same kind of energy you get when you light a match or strike flint on steel. On the atomic scale, it's gentle. Fission is something else entirely. When a slow neutron strikes a uranium-235 nucleus, the nucleus becomes unstable and splits in two. The fragments fly apart with roughly 200 million electron volts of kinetic energy, 50 million times what a chemical reaction can offer. You aren't rearranging atoms anymore. You're cracking them open and releasing the binding energy that has held them together since long before this planet existed. That energy has to go somewhere. Inside a reactor, it goes into the surrounding water as heat, atom by atom, billions of times per second. The water absorbs it, turns to steam under enormous pressure, drives a turbine, and a 7,800-ton submarine moves through the ocean at 20+ knots. That gap is the entire reason this works. The real question is why a submarine, of all the machines we could have put it in, was the first place we sent it. A submarine is the perfect machine for this fuel because of a problem every diesel boat has lived with since the day submarines first went to sea. A diesel engine burns fuel, but to burn fuel, it needs oxygen, and there's no oxygen at 300 feet down. So a diesel-electric submarine isn't really a submarine. It's a surface ship that submerges. To recharge its batteries, it has to come up, or extend a snorkel, a steel tube that pokes above the waves, so the engine can breathe. The snorkel is a periscope-sized object cutting a wake on the surface, hot with exhaust, visible to radar and infrared. For the few hours a diesel boat snorkels each day, it's the most detectable thing in the ocean. Uranium solves this completely. Fission does not need oxygen. The pressurized water reactor will run just as well at 600 feet as it does at 6. A nuclear submarine never has to surface for air, never has to snorkel. never has to expose itself to the sky. It can stay submerged for the entire patrol, limited only by how much food the crew can carry. Then there is the volume problem. Every cubic foot inside a submarine is contested. Fuel, weapons, sensors, crew, food, and water all want the same space. A diesel boat surrenders an enormous percentage of its hull to fuel tanks. A nuclear boat hands over a small compartment to a reactor and gets 30 years of range out of it. The physics of energy density does not care what you put it in, but the difference matters most where space and air are scarce. Underneath the ocean, both are. That fits on a pallet line earlier was honest, but it leaves the most interesting question unanswered. How much uranium is actually on that pallet, and how much of it really burns? A modern American submarine reactor core holds somewhere between 200 and 400 kilograms of uranium-235. Not a backpack, closer to a small refrigerator. And here is the part that surprises most people who learn it for the first time. Most of it gets consumed. Russian reprocessing data on spent naval fuel from facilities including the Mayak Production Association shows assays dropping from above 90% enrichment down to around 17%. The majority of the uranium-235A submarine sailed with is gone by the time the core is retired. So why pack so much in? Because of a problem you can't fix once the reactor is sealed. Every fission produces fragments: barium, krypton, xenon, iodine, and those fragments are neutron poisons. They sit inside the lattice and absorb the very neutrons the chain reaction needs. Xenon-135 is voracious. Without a counter strategy, the core would choke on its own waste in months. The counter strategy is brutal. Overbuild. Load enough uranium-235 on day one to keep the reaction critical for 30 years as fission products accumulate. Then add burnable neutron poisons, gadolinium, and boron, engineered to absorb extra neutrons early and deplete at almost the same rate the fission product poisons build up. The two curves cancel, so a submarine does not run on a tiny amount of uranium quietly burning while the rest stands by. It runs on a few hundred kilograms of uranium, most of which will eventually be fissioned, packed into a core so dense and so over-engineered that it can feed itself for 3 decades without a single mid-deployment refueling. The marvel is not that almost none of it burns. The marvel is that all of it, the whole 30-year fuel supply for a 7,800-ton warship, weighs less than a small motorcycle and fits in one sealed compartment. So when does a 30-year reactor actually die? Not from running out of uranium. There's still plenty of fissile material left when an American core is retired. Russian reprocessing data on spent submarine fuel showed discharge assays around 17% uranium-235, fuel that had started life above 90. Still fissile in absolute terms, but well below the enrichment a sub-sized pressurized water reactor needs to stay critical. Spent, by submarine standards. What ends the core's life is everything around the uranium. 30 years of neutron bombardment turns steel cladding brittle. 30 years of thermal cycling, heating up, cooling down, going to sea, coming home, stresses every weld in the pressure vessel. The limit isn't the fuel, it's the cage around the fuel. And here's the part the press releases don't say out loud. Even the cage is mostly fine. The 30-year figure isn't a hard physical wall. It's an engineering choice. The number Rickover's Naval Reactors branch picked as a conservative service life, with margin to spare, well before anything actually fails. The reactor, in principle, could go longer. The reason it doesn't is that by year 30, the submarine itself is at the end of its hull life. Sonars are outdated, weapons obsolete. The boat needs replacing anyway. The reactor was built to outlast the ship around it. So this is what it actually means for a nuclear submarine never to refuel. It is not a miracle of fuel economy. It is a marvel of engineering restraint. A reactor that could run longer, sealed inside a hull that will not. And all of it traces back to that one fact at the beginning. A few kilograms of uranium, fully split, can do the work of 1,000 truckloads of diesel. Once you have a fuel like that, the only question left is how long you want the ship around it to last.